Every single time you send a text message or, load up one of those endless social media feeds or save a massive file to the cloud, you are participating in this microscopic high-speed ballet of data.
Oh, absolutely. It's happening billions of times a second.
Right. And you probably expect that the systems handling all those simultaneous requests are running on the absolute cutting edge of modern computer science. I mean, the assumption is that the algorithms managing your data today were built specifically for the silent, lightning-fast hardware of the 2020s.
Which makes total sense to assume.
But the truth is, you are actually relying on a database architecture optimized by a mathematical trick invented way back in 1996. And the truly wild part about this, that trick was specifically designed to fix the physical, mechanical limitations of spinning metal hard drives. So, welcome to today's deep dive. Our mission is to uncover the hidden architecture powering the modern internet, an architecture that surprisingly dates back to a single academic paper published nearly 3 decades ago.
It really is a fascinating origin story. The insights we're unpacking today actually come from a highly detailed technical blog post that analyzes that seminal 1996 paper.
Yeah, the paper is titled The Log-Structured Merge Tree, or as we'll call it for short, the LSM-Tree.
Exactly. And the original research was conducted by Patrick O'Neill, Edward O'Neill, and Gerhard Weikum. But, what's particularly interesting about our source material today is that the blog post breaking all this down was co-written with Anti-Gravity.
Wait, Anti-Gravity, the AI?
Yeah, the AI pair programmer developed by the Google DeepMind team. So we essentially have modern artificial intelligence helping to decode the 1996 architecture that, makes modern artificial intelligence possible.
Okay, let's unpack this. Because to understand why this specific paper changed the foundation of the internet forever, we really have to take you back to 1996.
Right, time travel back to the 90s.
We have to completely forget about the solid-state drives or SSDs that are in your laptop or your phone today. Back then, SSDs simply didn't exist in production servers. If a system wanted to store data permanently, it had to write it to a hard disk drive, an HDD.
And those were literally mechanical devices.
Yes. They have a physical metal platter that physically spins and a tiny mechanical read-write head mounted on an actuator arm that has to physically jerk across the disk to find the right magnetic sector.
And that physical reality is the entire genesis of the problem. It's mechanics, plain and simple. And mechanics take time.
They really do.
When traditional databases in 1996 needed to save or update information, they mostly relied on a data structure called a B-tree. Now, B-trees are fantastic for retrieving data quickly because they keep everything organized and balanced.
But there's a catch, right?
A huge catch. They have a fatal flaw when it comes to writing new data. They update information in place.
In place. Meaning what exactly?
Meaning, if you change a user's record, the database has to command that mechanical disk head to physically seek out that exact user's specific page on the spinning platter, wait for the platter to rotate, and overwrite the data right there.
Oh man, that physical movement is agonizingly slow in computer time. According to the source, a random disk seek takes about 10 milliseconds.
Yep, 10 milliseconds.
Now, 10 milliseconds sounds instantaneous to a human being. But to a computer, it means you are physically capped at around 100 random write operations per second.
Which is incredibly restrictive.
Think about that limitation. Imagine you're writing a diary, but every time you want to add a new thought, you have to randomly flip to page 47, carefully erase a line, write a new one, then randomly flip to page 112 to do the exact same thing.
That sounds exhausting.
It is. That is a B-tree operating on a hard drive. You're spending all your time flipping pages instead of actually writing down your thoughts. If you're dealing with write-heavy workloads, like a server ingesting thousands of event logs or telemetry data from sensors or handling millions of global financial transactions, that physical page flipping creates a massive system-crashing bottleneck.
What's fascinating here is how the researchers looked at this physical limitation. They didn't just accept the 100 writes per second cap.
Right.
They realized that while random writes were terrible, sequential writes were a totally different story. If you just lay the data down continuously as the disk spins without ever moving the mechanical head back and forth, you achieve orders of magnitude higher throughput.
Because the hardware isn't jerking around anymore.
Exactly. The disk head just parks in one place, the platter spins smoothly under it, and you write a continuous, unbroken stream of data. So the 1996 paper asked a radical question. How can we arrange our data so that we only ever write to the disk sequentially, but still keep everything perfectly sorted and instantly searchable for the users.
Which feels like a total contradiction. I mean, if you just blindly dump data onto a disk sequentially as it arrives, you just end up with a chaotic, unsorted pile of information.
A complete mess, yeah.
How do you find a specific user's profile later without scanning the entire drive? Since we know we can't write randomly to the hard drive without killing our performance, the engineers realized they had to intercept the data before it ever touched the physical disk.
And that realization is the core brilliance of the LSM-Tree. The paper proposed dividing the database into two distinct cooperative parts. They called them the C0 component and the C1 component.
Okay, C0 and C1. Let's break those down.
Sure. The C0 component lives entirely in volatile memory, or RAM, and the C1 component lives on the persistent, durable hard disk.
So let's look at that C0 component first. Data comes into the server, and instead of going straight to the mechanical hard drive, it goes straight into RAM. And RAM has no moving parts whatsoever.
None at all.
There's no physical seek penalty, no spinning platter, so these writes are finishing in nanoseconds. Inside C0, the database builds a dynamic sorted index. The source notes it's usually something like a self-balancing memory structure, so it constantly reorganizes itself to stay searchable.
Right, and both the key, let's say the user's ID, and the value, like their profile data, are stored right there together.
So C0 acts like a sponge. It absorbs all the incoming traffic instantly and keeps it perfectly sorted in memory.
And then we have the other half of the equation, the C1 component. This is the permanent home for the bulk of the database on the hard disk. It's a massive read-optimized index, structurally similar to that B tree we talked about earlier.
But with one big difference, right?
One absolute critical difference.
Yeah.
It is laid out completely sequentially on the disk. It is block-aligned and perfectly contiguous.
Wait a minute, hold on. I see a huge flaw here.
Oh, what's that?
Well, RAM is volatile. It requires constant electricity to hold data. If a server loses power or, I don't know, a technician accidentally trips over the power cord, doesn't that entire in-memory C0 tree just vanish into thin air?
It does.
You'd lose all your most recent critical data. And furthermore, inside RAM, data is connected by virtual memory addresses. They're just temporary pointers to spots in the volatile memory. If the machine restarts, those virtual addresses become completely meaningless.
That's entirely true.
So how on earth do you take a virtual tree floating in RAM and translate it to a permanent physical disk without the whole structure falling apart?
That is exactly the hurdle the authors had to clear. I mean, how do you serialize a virtual dynamic tree into physical permanent storage without corrupting it? They solved this translation problem with two key mechanisms.
Okay, let's hear them.
First is pointer-to-offset translation. When data moves from the volatile C0 tree in RAM down to the durable C1 tree on the disk, the system strips away all those temporary virtual memory pointers.
And replaces them with what?
It replaces them with exact physical file byte offsets.
Oh, I see. So instead of a pointer saying, go to this temporary memory address, it's mapping the data to a literal physical geography on the disk itself.
Precisely. The disk index literally says the child block for this data starts exactly at byte offset 40,960 in the file.
Wow, that's incredibly specific.
It has to be. Now, to write this geography to the disk without triggering those dreaded random seek times, they used a second technique called bottom-up sequential writing, or sometimes it's called bulk loading.
Okay, how does that work?
When it is time to save everything to the disk, the engine doesn't start at the top of the tree. It starts at the very bottom. It takes the leaf blocks, the actual raw data values, and rakes them to the disk continuously in one smooth sequential stream.
Nice and fast.
Exactly. And as it writes them, it records their physical byte offsets. Then, it constructs the parent index blocks in RAM, embedding those newly recorded physical offsets into the parent blocks.
Oh, clever.
Yeah. Once built, it streams those parent blocks sequentially to the disk, right after the leaves. It cascades this process all the way up until a single final root block is written last.
That makes so much sense. It is basically building the structure from the foundation up. It writes down the permanent address of every room as it builds it, and then hands you the master directory at the very end.
That's a great way to look at it.
But that brings us to the next massive problem. We have this lightning-fast C0 in RAM absorbing all the traffic, and this highly organized C1 on the disk. But RAM is wildly expensive and finite compared to hard drives.
Very true.
Eventually, your C0 memory buffer is going to fill up. You will run out of space. So how do we move all this accumulated sorted data from RAM down to the disk without suddenly causing the exact random disk seeks you just spent all this effort trying to avoid?
All right, and this is where we get into the absolute heart of the LSM-Tree engine. It's called the rolling merge.
The rolling merge.
Yes. The engine never, ever tries to load the whole massive data set into RAM to figure out how to combine it. That would immediately crash the server. Instead, it uses a technique called external merge sorting. It treats the data as a streaming process.
Let me try an analogy here to visualize this. It's like a traffic zipper merge.
Oh, I like that.
Imagine you have two perfectly organized lines of cars merging onto a single-lane highway. One line of cars is coming from the local road, that's our new data in C0. The other line of cars is already on the highway, that's our old data in C1.
Right.
You don't need to build a massive parking lot to hold all the cars at once to figure out who goes next. You just stand right at the merge point, look at the two cars at the very front of the lines, and wave forward whichever car comes next alphabetically by its license plate.
Exactly.
You can sort and merge millions of cars perfectly, but you only ever need enough physical space to look at two cars at a time.
That is a phenomenal way to picture external merge sorting. In the database, the engine opens a sorted iterator for the C0 data in memory, and it opens a buffered reader for the C1 data on the disk.
Okay, so it's looking at both streams.
Right. And here's the magic trick. That buffered reader only loads a tiny 64 kilobyte block of C1 into RAM at any given time. The engine simply compares the heads of both streams, the keys at the very front.
Just like looking at the two cars in front.
Exactly. It takes the smaller key, writes it to a brand new temporary file on the disk using a 64 kilobyte buffered writer, and discards any stale duplicate data along the way.
So because it is only looking at 64 kilobytes of the old disk file and holding 64 kilobytes of the new disk file in memory at once, the memory footprint of this entire massive sorting operation never grows.
It doesn't. It is strictly constant.
It only takes memory equal to the size of two single blocks. We are talking about maybe 128 kilobytes of RAM being used to execute this merge.
Let that sink in. You could be merging terabytes or even petabytes of data, and the algorithm only strictly requires a little over 100 kilobytes of working memory.
That is just mind-blowing efficiency.
And because you were just reading the old file straight through and writing the new file straight through, it guarantees pure sequential I/O. The mechanical disk head is just gliding along smoothly at maximum physical speed.
No random jumping around.
None. Furthermore, this provides tremendous safety. All this merging happens into a temporary file. When the merge is 100% finished and mathematically verified, the engine does a simple file rename to replace the old files.
So it's totally atomic.
Exactly. This guarantees that a file is never left half-written. If the power dies mid-merge, the database just deletes the half-finished temporary file on reboot and tries again. Nothing is ever corrupted.
Okay, that solves the power failure issue during the merge perfectly, but let's look at the bigger picture. The two-component model C0 and C1 works beautifully for a while. But what happens when the database gets really, really big over years of use? Say your C1 disk file has grown to 100 gigabytes, and your C0 RAM buffer is only 10 megabytes.
Okay, I see where you're going.
When RAM fills up, merging 10 megabytes of fresh data into a 100 gigabyte behemoth means you have to sequentially read and rewrite all 100 gigabytes just to add that tiny little 10 megabyte sliver. Doesn't that just create a massive traffic jam on the disk anyway?
You've hit on the exact systemic flaw that required the next evolution of the design. What you are describing is a phenomenon known as write amplification.
Write amplification, okay.
To use your zipper merge analogy, imagine doing that perfect zipper merge, but one lane has 10 cars and the other lane has 1,000,000 cars. You are forcing 1,000,000 cars to stop, drive through the checkpoint, and re-emerge just to let 10 local cars onto the highway.
That sounds incredibly wasteful.
It wastes massive amounts of disk bandwidth. To solve this, the 1996 paper didn't stop at two components. It generalized the design into a multi-component LSM-Tree. Instead of just C0 and C1, you have C0, C1, C2, cascading all the way down to a final swake.
So instead of flushing the small RAM buffer directly into the giant final disk index, the data cascades down through intermediate tiers over time, almost like a waterfall.
Exactly like a waterfall. When C0 fills up, it merges into a very small C1 component on the disk. When C1 reaches a certain size limit, say 100 megabytes, it triggers a separate background rolling merge into C2, which might be capped at 1 gigabyte.
And it just keeps flowing down.
This flow continues down to the largest final component. Implementations usually keep the size ratio between adjacent tiers to a strict factor of 10. By keeping the size differences relatively small between any two adjacent components, you dramatically reduce that write amplification penalty.
I follow the cascading logic, but there is a glaring operational question here.
Okay, what is it?
If we are only ever appending data sequentially and we never overwrite records in place like a B-tree does, how do we delete a user's account? We can't just command the disk head to seek to their record and erase it.
That is a crucial point. You are right, you cannot erase in place. Instead, the LSM-Tree issues a tombstone.
A tombstone?
Yes. A tombstone is a special deletion marker. If a user deletes their account, the database inserts a tombstone record for that user ID into the C0 RAM buffer, just like a regular write.
So you write a deletion?
Exactly. As a rolling merges happen, that tombstone cascades down the tiers. Whenever a merge process sees the tombstone and the old existing data in the same merge window, the tombstone effectively annihilates the old data.
Oh, wow.
Neither the old data nor the tombstone is written to the new file. Over time, deletions chase down the obsolete data and organically clean the system.
That is fascinating. It's like issuing a death certificate that eventually catches up to the record.
Pretty morbid, but yeah, that's exactly it.
But what about updates? If I am a user and I update my profile picture 3 times in one single day, my data is cascading down through all these different tiers at different speeds. How does the database know which version is the correct final one? Did they use timestamps or sequence IDs back in 1996 to keep track of all these versions?
This is a really common misconception. The original 1996 academic paper did not use sequence IDs or transaction timestamps, or what modern developers call multi-version concurrency control.
Really? Then how do they do it?
It relied entirely on physical location. The logic was foolproof because all writes always enter C0 in RAM first. Any data found in C0 is definitively newer than data in C1.
Oh, of course.
And data in C1 is definitively newer than data in C2. So during a rolling merge, if the engine finds the exact same user ID in both components, the value from the upper newer tier simply overwrites the lower tier.
And the older version is permanently thrown away?
Exactly. The concept of sequence numbers, which allow modern databases to keep track of historical versions to take snapshots, wasn't formally integrated into LSM trees until industrial implementations came along years later.
Which perfectly sets up how we actually get data out of this system. We have successfully stored everything sequentially. The writes are incredibly fast. But if an application requests a single user profile, how does the database quickly retrieve that record across all these different cascading layers without scanning everything?
Well, the read path is essentially the exact reverse of the write lifecycle. To look up a key, the engine searches the volatile CO tree in RAM first.
But because it's the freshest.
Right. Because CO naturally holds the absolute freshest data. If the key or a tombstone is found there, the engine returns the result immediately and stops looking entirely.
So it doesn't even bother checking the disks.
Nope. This naturally guarantees that readers always see the most up-to-date value, even if a dozen older versions of that profile are sitting down in C4 waiting to be wiped out in a future merge.
And if the record isn't in RAM,
then the search moves down the chain. It searches C1, then C2. Now, scanning multiple disk files sequentially could get unacceptably slow. So modern implementations heavily utilize something called Bloom filters.
Ah, Bloom filters.
Yeah. A Bloom filter is a highly space-efficient mathematical data structure. Its only job is to tell you very quickly if a specific key is definitely not in a file.
So it's like a fast pass for skipping useless searches.
That's a great way to put it. The database can instantly skip searching any disk components that don't contain your data, saving immense amounts of time.
Here's where it gets really interesting to me. The read and write paths we just described, they were explicitly designed in 1996 to fix the slow physical movement of a spinning metal disk heads.
Yes, the mechanical bottlenecks.
But fast forward to today, the servers powering the cloud use SSDs and NVMe flash drives. There are no moving parts anymore. There is no metal platter. You would logically think the LSM-Tree would be totally obsolete.
You really would.
But instead, it is the undisputed king of modern databases. If we look at the timeline from our source material, it's wild. In 1996, O'Neill and his team established the C0 and C1 sequential merge model. 10 years later, the internet is exploding.
The Web 2.0 boom.
Right. The amount of data being generated daily is staggering. Google has to manage this unprecedented scale, so in 2006 they released Bigtable, and shortly after, we get Apache Cassandra.
Massive milestones.
They take the 1996 paper and modernize the C0 and C1 model into what they called mem tables and S tables. They also solved that power failure vulnerability we discussed earlier by fully integrating a write-ahead log, a wall.
Ah, the wall, yeah.
That is a tiny sequential log appended to the disk right before C0 was updated, just to guarantee durability if the power fails before the RAM flushes.
And the industrial innovation didn't stop there. By 2011, Google engineers refined this architecture further into LevelDB. They introduced structured leveled compaction and baked those Bloom filters right into the core architecture to speed up reads.
It just kept evolving.
It did. Then, in 2013, Meta, which was dealing with unprecedented high concurrency for billions of Facebook users, forked LevelDB to create RocksDB. They optimized it for aggressive, multi-threaded background flushes.
And RocksDB is huge now.
Huge. Today, RocksDB is practically the default storage engine for the entire internet. And in 2016, a paper called Whiskey introduced key-value separation.
What's that do?
They realized that for modern SSDs, you can reduce write amplification even more by only keeping the keys in the cascading tree levels and storing the actual bulky data values separately in an append-only log.
Wow.
If we connect this to the bigger picture, it reveals a profound truth about computer science. The core belief of the 1996 paper prioritizing sequential I/O over in-place updates proved that software algorithms can actually conquer hardware physics.
Even when the hardware changes completely.
Exactly. Flash memory on a modern SSD wears out and degrades if you randomly overwrite the exact same block too many times. B-trees destroy SSDs over time. But the LSM-Tree's purely sequential append-only design. It perfectly anticipated the optimal way to write to flash memory, a full decade before flash memory was even a standard technology in data centers.
So what does this all mean for you, the listener? It means that out of the random chaos of a billion people furiously clicking, typing, liking, and uploading all at the exact same moment, the LSM-Tree acts as a magical funnel.
A very organized funnel.
It organizes that random chaos into a perfectly ordered sequential stream. It allows modern databases to scale to terabytes or even petabytes using only kilobytes of active working memory. It is a mathematical masterpiece, quietly running behind the scenes of almost every app on your phone today.
It truly is the architectural foundation of the modern data-driven world, just hiding in plain sight.
And that leaves us with a final thought for you to mull over. The LSM-Tree was a software workaround for a physical hardware limitation, the spinning metal disks of the 90s. Today, it rules the silicon of our solid-state drives. But hardware is about to fundamentally change again. We have quantum memory on the horizon. We have researchers successfully encoding massive amounts of data into synthetic DNA storage.
It's incredible stuff.
When the very physical nature of how we store information changes, the software algorithms will inevitably have to change with it. It really makes you wonder what seemingly obscure, hyper-technical academic paper is being written right now in some quiet university lab that will dictate the hidden architecture of the internet 30 years in our future. Until we find out, keep digging.